So today we are going to start with another new topic called plane stress and plane strain. Okay, so this is another very important topic. Along with this topic we will see the generalized Hooke's law, which is in 3D, and how the basic transformation of plane takes place, and what are the examples of the applications of plane stress, what are the applications of plane strain, then how they are connected with an generalized Hooke's law. Okay, then further we will proceed with an Airys stress function. Okay, so that is also a very important topic. So how you can differentiate the Airys stress function with an plane stress and plane strain. So today our agenda is all about this particular topic. So before starting, I will just give a glance of when a load is acting to an any plane, okay, or any object, right? Considering a small elemental portion, right? So how this, due to the further addition of load, how there is a transformation of load, okay? How the transformation or the principal axis, or how it get transformed. Okay, so we have to see both for the stress and the strain. Okay, so for that, so whenever the load is acting, it is transformed into a new plane consists of the sigma x prime, sigma y prime, and tau prime. Okay, tau prime. So you have to find out sigma x prime equals to sigma x. So here we'll be having sigma x, this will be sigma y, and this one is a tau. So in that case, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau sine 2 theta. Okay. So you will know what is a transformation of the plane at what angle. If this plane is deflecting downwards, the theta value will be considered as negative. If the plane is deflecting upward direction, right, along this direction, or plane is moving along this plane, we'll call as a positive theta, and if it is moving along this way, negative. So you will know what is the theta value will be given. You can substitute the value, you will get the sigma x prime. Similarly, we can find sigma y prime, sigma x plus sigma y by 2. Now what I am going to do is I am going to take negative, other factors will remain same, negative sigma x minus sigma y by 2 cos 2 theta plus tau sine 2 theta. Okay. Next we will find tau prime. To find the tau prime, we have to use this formula. Sorry, it will be tau prime minus sigma x minus sigma y by 2 sine 2 theta plus tau cos 2. This will be the formula. Yes.
Ma'am, I didn't understand the concept. What is happening here?
Already we have done. We have explained.
Ma'am, is it the case of biaxial and pure shear stress?
Yes, biaxial stresses, and also the pure shear. Yeah, pure shear conditions. Now when it is transforming to a new plane, right? So previously we have found out what is a normal stress and what is the shear stress, pure shear, we have found
Yes,
out.
yes.
But here, how these stresses are changing. Here the main motto is to find out the how the stresses when it is deflecting at an angle maybe of 20 degree, right? How this sigma across this plane is changing, right? Here this is not a principal plane, right? Principal plane, we have seen what is a principal plane, maximum principal plane, where the shear stress will be 0, right? So by changing each and every point, right, we are going to check that which plane the shear stress was going to be 0. That plane will become the principal plane, right? But here we are seeing the transformation. So when this, due to this loading, how this particular molecule, so we have taken this complete big uh, one bar, and from the bar we are having some tensile force, okay, right? Now next another bar they have taken as a cantilever beam, and there is some point load acting. Now let's take a small element in that point, in the complete beam, right? So in the small element, what kind of stresses and shear stresses acting on that particular point, that is the main thing. Due to the further loading, how it is reacting, what will be the new form of sigma, what will be a new form of sigma y and tau, right? So that is the main motto over here to find out, okay? So
Yes,
similarly,
sir.
similarly we can find out what is a strain for an this particular system, okay? So we know initially if corresponding to this value, we will have a strain of sigma x, epsilon x, then corresponding to this value will have the epsilon y, right? Corresponding to tau we will have the gamma xy, okay? So if we merge that, so we can find out the equation like sigma epsilon x prime equals to sigma x, epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta, okay? Similarly, instead of this tau, it has been just transformed by gamma xy y, okay? Next, epsilon y prime becomes epsilon x plus epsilon y by 2. Again they have got minus of, if you take common over here, it will become plus, right? So epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta, close the bracket. And similarly further here also we'll have the gamma xy by 2 equals to epsilon x minus epsilon y by 2 sin 2 theta plus gamma xy by 2 cos 2 theta. You have to remember this formula. Sometimes they will give you this plane. What they will do is they will give you a schematic diagram of this plane, and they will ask you to find out the what is a transformation, okay? What is a transformation? So you have to calculate using these formulas, and you have to find out the correct answer.
Ma'am,
Yes, please.
still
Yeah, tell me.
in the third diagram, third diagram, why sigma y direction is changed, ma'am? It
Sigma,
is compressed
which direction?
y dash.
No.
It is in inward, ma'am, but in second.
No, it is just a figure. It's not a matter, right? It will be like this. It shows a compressive in nature, right? It's just a figure.
Yes, ma'am.
Okay, just a figure I have taken. So to represent that how it's transforming the plane, right? So but here I am considering it's all at the tensile. But if there is a compressive, as in this figure it shows compressive in nature, then once you substitute, then the sigma y value will be negative of that value, right?
Yeah.
It is just a uh, uh, nature, just a nature.
Was it misprint, ma'am?
Was it?
Misprint, I mean symbol,
No,
that direction.
see. This figure I have just taken for understanding purpose. Okay. So to explain in behalf of this diagram, right? It doesn't relate with this equation. I just want to compare you that how this thing happened. Okay. It is nothing about the misprint or something. Okay. Suppose it is of negative, then I have to consider as a negative. The value when I will be substituting, I have to just substitute in
Yeah.
terms of negative. That's all.
Minus sigma. Okay.
Okay, that's all.
Okay.
Okay. Now coming to another very important point called as a generalized Hooke's law. Okay. So here you have to remember, so this is another very important topic. Okay. So here again we'll be having some kind of matrix formulas. Okay. So generalized Hooke's law is actually the Hooke's law what you have studied, that is a stress is directly proportional to the strain within an elastic limit. So we can write sigma is equals to E epsilon, right? Now this is for 2D condition. In 3D we will be having, so consider any 3D object. Okay, so here you can see in this figure, so a small cube. So this small cube will be subjected to any sort of load, right? For each and every plane it will undergo its stresses, and along with the plane, along the plane. So here they have considered that one direction, like how this stresses is going to occur. So this magnitude has been said in the form of matrix, that is sigma equals to S into epsilon. Okay. Now this S is known as an stiffness matrix. Okay. S is known as an stiffness matrix. Right. Now we will see how this property, when this load is acting on it or the stresses is acting in all those planes, right, 3 different planes, how this property changes and each and every point. Okay, so here when we are considering this kind of thing, this is a 3 cross 3 matrices. Okay, so what are the loads we are having? So what are the stresses we will be having? We will be having around 9 stresses. We are having around 9 stresses, and due to this 9 stresses, it will undergo 9 strain. It will undergo 9 strain. Now to find out this strain value, it can be also be written as in this form: epsilon equals to C sigma. Okay, epsilon equals to C sigma, and where the C is called as a compliance matrix. Okay, C is known as an C is known as a compliance matrix. Now we will see, so how I can relate the C and S. How I can relate C and S. So if I have to relate in this equation, so what will I write? If epsilon equals to 1 by E into sigma, right? If I have to write from this equation. Now here when I am writing this equation in terms of matrix form, right? So epsilon equals to C into sigma. Then how this C, that is a compliance matrix, and stiffness matrix are related? How they are related?
Inverse, ma'am.
So can I say S equals to C inverse? That is, stiffness matrix is an inverse of an compliance matrix, right? So please remember that. Now we will see that as I've said, that what are the stresses? 9 stresses, right? So what are the 9 stresses? Sigma xx, sigma xy, sigma xz, right? Sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, and sigma zz. So we are having 9 stresses and similarly 9 strain. Okay. Now you need to remember one more important thing, right? So this, if they are asking about the stresses and strain, these are the second order of tensor. Just remember the word, right? Second order of tensor. But if they're asking about the stiffness matrix and the compliance matrix, they are the fourth order of tensor. Okay, fourth order. Please note down. So stress tensor and the strength tensor are of second order, and the stiffness and the compliance matrix are of the fourth order. Okay, can I change? Have you noted the things? Shall I change?
Ma'am, 1 second. One
Okay.
second,
One second,
ma'am.
ma'am.
Okay. And remember this, some of the textbook they are writing in a different conventions. Okay, so conventions again is not a matter, but remember the facts, right? What it is happening over here. Okay, just remember the fact that is happening, and the name remains same. When you're using this formula, the whatever the factor they consider, it should be a stiffness matrix, and in this case it will be the compliance matrix. Okay, once you're done, just let me know.
Yes, ma'am, completed.
Okay, right. So now we will see this, the matrix form, right? In the matrix form, how these things are occurring. So we will take the major stresses. Okay, major stresses. So we will take the 6 components of the stress and 6 component of the strain, right? So here in this, okay, these are the formula, right? So please write down this formula. Okay, that is, here we have sigma equals to S into epsilon. These are the S. S is for stiffness matrix. Okay. As I've said, the convention doesn't matter, right? So just remember that. Now how many cells are there, or how many elements are there in this stiffness matrix? Can you tell me? How many cells are there, or how many elements are there in this stiffness
36.
matrix? Yes, we have 36 elements. Okay, so that means where all the properties, each and every properties are heterogeneous. Okay, so in that cases we have the we call as a elastic constant is 36, right? Now if I consider that sigma ij is equal to sigma ji, right? Now for an example, if I consider sigma 1 2 is equal to sigma 2 1, sigma 1 3 equal to sigma 3 1, sigma 1 4 equal to s 1 4 equals to s 4 1, s 1 5 equals to s 5 1, s 1 6 equals to s 6 1, right? Now if I keep on doing this, like s 2 4 will represent s 4 2, s 2 3 will represent s 3 2, right? If I keep on doing likewise, that applying this condition, like if sigma ij equals to sigma ji, right? So on that condition, what will be the number of elastic component or elastic uh, independent constant? Please calculate and tell me. If sigma ij equals to sigma ji, or I can say sigma s ij equals to s ji. If this is a fact, calculate and tell me. How many you are getting?
1.
Yes. How many you are getting? Are you getting 21? Are you getting 21? So when there is a symmetric matrix, right? When there is a symmetric matrix, this is called as a symmetric matrix. Okay. So in the symmetric matrix, you will be having 21 stiffness component, which is actually independent, or I can say 21 independent stiffness component, okay, for a symmetric matrix, right? Shall I skip? Just let me know. Okay. And one more thing, in some of the textbook you can also find this kind of conventions here: sigma xx, sigma yy, sigma zz, okay, or tau xy, tau yz, and tau zx. Okay, so either of this convention is also correct. Okay, either of this convention is also correct. Shall I skip? Just let me know.
Yes, ma'am.
Okay. So as I've said, you will get some kind of this kind of thing, matrices. So stiffness matrix for a linear anisotropic material. Okay. So you will get 21 independent elastic constant. Now moving to an orthotropic condition. Yes.
Excuse me. Ma'am, other than this, like substituting, don't we have like any other formula like direct to calculate constants?
I will come to that. I will
Okay.
come. Okay. So
Okay,
next we have another form. Just give me a second. Can you see my screen?
Yes, ma'am.
Yeah, it is visible, right? It's a plane. Okay, fine.
Yes, ma'am.
Okay. Now we will have for an orthotropic material. Okay. Okay. So let me write a compliance matrix, okay, for an orthotropic material. So we'll write something like that: epsilon xx, epsilon yy, epsilon z, gamma xy, gamma yz, and gamma zx. So sometimes in the question, right, they will ask you that how many number of elastic constant are there. So this kind of question you can expect. And in case of orthotropic material, you will be having 9 elastic constant. Okay, you will be having 9 elastic constant. Another material they can ask as a monoclinic. Okay, monoclinic. Just remember, for monoclinic we will be having 13 independent elastic constant. For monoclinic we will be having 13 independent elastic constant. For orthotropic we will be having 9 independent elastic constant. This will be the formula. This is the for the compliance matrix I am writing. Okay, 1 by Exx, then minus mu by Eyy, then minus mu by Ezz. So you have to remember this matrices, okay, because they can ask a problem based on this matrix. This means mu zx e power zz, and have 0 0 0. Then again we'll have corresponding to this have minus mu xy, then Exx 1 by Eyy minus mu xy, sorry, zy Ezz 0 0 0. Okay, we have minus z by Exx minus mu y z by y. Here we have 1 by z 0 0 0. Here we'll have zeros, and 1 by 2 rigidity modulus of yz. Here 0 0. Here we have 0. Again 1 by twice of rigidity modulus around the zx. Okay. Here we'll have another 1 by 2 gxy. So what matrix is this? It's a stiffness or compliance matrix. Tell me that. What matrix is this?
Compliance, ma'am.
Compliance matrix. Okay. So what kind of question you can expect from this? So in the exam point of view, they will give you this kind of matrices, okay, and so you have to identify that which matrices they have given. So there will be, now this is the, what I am showing you is an orthotropic, so you have to identify based on number of independent elastic constant. Okay, first thing is you have to identify using the number of elastic constant. Then you have to see that formation. If the formation is like this, epsilon, then you have this whatever the matrix, and you have the sigma, that means you have to understand this is a compliance matrix. Okay, that particular form you have to remember. Now they will ask you, they will give you some of the random values, and from the random values you have to find out what is the formula, or what will be the formation of that particular thing. Anyone, they might ask you what will be the constant term for this, okay, or what will be the constant term for this particular one, right? So you should know that how to find out the value for this. Okay, now for an example, if they ask you to find out for an epsilon zz, okay, now how you can find? So simply I can write this for epsilon z, that it is nothing but sigma z by ez, right? So I will know what is the matrix over here and what will be the value over here, so I can simply calculate and I can tell the answer, right? Or they might ask you this form, that what will be the gamma xy. Now for the gamma xy, they will give you this random values, right? So I can write this gamma xy is that tau xy by 2 into g yz, right? I can write. So likewise you have to figure out the values. Okay, they will give you the matrix and they will ask you to find out the unknown parameters. Alright, clear? So next we will move for the isotropic material. Okay, the main thing we will be working on the isotropic material, right? So isotropic material will be having the two constants. Okay, two independent constants. So shall I rub this part? Just let me know, can I rub this or no? Can I? Just let me know.
Ma'am, for
Yes?
11,
Yes, yes.
ma'am, how do we should remember this, ma'am, like 9 elastic constants are there
Yes,
in ortho.
absolutely. You have to remember the matrix because I will show you in the upcoming slide. Just let me show you some of the problems. Okay, so they will give you some kind of matrices like this. You can see, right? So they will
Yes, ma'am.
ask you to find out, predict that what will be the b value. Okay, so you should know what is a b value. So if I ask that what is a b value here, then you should able to say that 1 by twice of g of that value, right? So you should know that form. Okay, so you should know that form, that what is the b value, what is a value, what is c value. Okay.
Then, ma'am, there are many different types now, ma'am, like orthotropic, monoclinic,
Hmm.
biclinic. Some there are many, ma'am.
Triclinic,
Like
triclinic. So
yeah,
triclinic and anisotropic will be having almost same constant, that is 21 independent elastic constant will be there. Okay, then comes monoclinic. Monoclinic will be having 13 independent constant. Then comes orthotropic. Ortho will be having 9 constant, and then comes your isotropic. Okay, isotropic will be having 2 constant. So here you see in this question they have mentioned the isotropic material. Okay,
yes,
they
ma'am.
will be mentioning you. So based on the understanding you have to substitute the value. So they will give, there are a lot many possibilities that how they can ask you the question. Okay, so here they have given you this a b c d, they have not given you in terms of any other equation. Okay, so you
Yes.
have to find out the value, what is that value, and based on that we'll come to this problem. Okay, we after explaining you everything, I will come to this problem, that how to solve this kind of problems. Okay,
Okay.
right, now shall I erase everything? Now I will move for the isotropic material. Okay, right. Now for an isotropic material, because that will play a very important role, because when we will see for the plane stress or plane strain, we will look for the isotropic material only. Okay, so for an isotropic material you have to remember both the stiffness matrix and as well as a compliance matrix. Okay, so the formula is something like this: sigma x, sigma y, sigma z, tau xy, tau yz, tau zx. Now this equation will be something a bit different. Have E by 1 plus mu and 1 minus of twice of mu. Okay. So here what is mu? Mu is an Poisson ratio. Okay, ratio between the lateral strain by the longitudinal strain. E is a Young's modulus into 1 minus of mu, then mu, then mu, 0, 0, 0. Since here mu, here also will be having mu. Here will have 1 minus mu. Here also will be having mu. 0, 0, 0. Okay. Again we'll have here mu. Here we'll have mu. Here we'll have 1 minus of mu. 0, 0, 0. Okay. Now remaining in this lower half, everything will be 0 except this diagonal elements. Except this diagonal elements. Okay. So here we'll have 0, 0, here we'll have around this point 0, so 0, okay, 0, 0, 0, 0, 0, 0. Okay. Now what will be these components? Here we'll be having 1 minus 2 mu by 2. Same here, 1 minus 2 mu by 2. Here we'll also have 1 minus 2 mu by 2. Okay. Close the bracket, and here we'll have epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma zx. Alright.
Ma'am, it is for isotropic material.
Sorry, it is for?
Ma'am, is it the case for isotropic material?
This is for isotropic material, exactly. This is for isotropic material. Okay. So you will be having the number of independent elastic constant is 2. Okay, here number of elastic constant will be 2. These are the numbers you have to remember. So once you are done, just let me know, then I will move for the compliance matrix.
I have copied it, ma'am.
Okay, so all of you have copied?
Yes, ma'am.
Okay, now let me erase and we can start. Now what is the compliance matrix? Okay, so compliance matrix is epsilon c and then we'll have sigma, right? Now how we can write this? Epsilon xx, epsilon yy, epsilon zz, then gamma xy, gamma yz, and gamma zx.
Excuse me, ma'am.
Mm-hmm.
Ma'am, generally the stiffness matrix is represented by C and compliance matrix is represented by S, right, ma'am?
See, there's a lot many confusions. So I don't prefer like this. You just need to remember what is this matrix, right? So when there is an inverse, it is a compliance.
Compliance, yes, ma'am.
Okay, and when there is this is a form, right? Sorry.
Sigma is equal to.
So I consider it's as stiffness. So
Oh.
that's all is need to remember, right? Because each textbook they represent in a different way.
Okay,
Right?
because in KCO book, in composite book, it is represented in the inverse manner, ma'am.
Okay.
So
Alright.
only I just
So,
got the
yeah,
confusion.
yeah. So at the beginning of the class itself, I said like it depends. It varies actually. In different textbook they have written K. Some textbook they have written S, right? So for avoiding, right, it varies, right?
Okay,
But
ma'am.
the matrices will be like stiffness for that, and the inverse one will be the compliance. Okay.
Yeah, yes, ma'am.
So 1 by E, open the bracket, right? Now corresponding to this one will be having 1, then minus mu. Mu is a Poisson's ratio, then again minus mu. So since this is mu, this term will also becomes minus mu 1, and here again becomes again minus mu. This would be zeros. Okay. Similarly, this one will become again minus mu 1. 0 0 0. Okay. Now again this particular bottom term will be 0, right? This diagonal part will only be active. So let's see what is the diagonal values. This value is twice of 1 plus mu. Twice of 1 plus mu. This is 0 0. Then similarly this will be twice of 1 plus mu 0 0 0. This will be twice of 1 plus of mu. Right? And here we'll have sigma xx, sigma yy, sigma z, then tau xy, tau yz, and tau zx. Now similarly the same question can appear over here. Same kind of questions can rise. Now if they ask to find what will be the for an example, sigma yy, sorry, epsilon yy. Now what will be the value if I need to find epsilon yy? Now what will be the value for epsilon yy? Tell me the value. What is epsilon yy?
Ma'am, sigma yy by v.
Which one?
Epsilon yy is equal to sigma yy by v.
Can I say one of the form like minus mu, right? Sigma xx by e, right? If I have to write another way, sigma yy will become sigma epsilon yy by e, right? Next I can also write epsilon yy becomes minus mu sigma zz by e. Can I write?
Yeah.
Right? So if I want to find what is the value of mu from here, so what is the value of mu? I can find out. That is minus epsilon yy e by sigma xx minus of. Similarly, that can be equal to epsilon yy e by 0 zz. Right? So you have to be well aware about these facts. Okay? They can ask in any random way. They can ask in any random way. Right? Clear? Shall I change the slide? Yes, yes.
Without solving this 6 by 6 matrix, how can we straight away say this, ma'am? I don't understand this.
Without
Yes, ma'am. It's like very complicated.
without solving. So this is a huge derivation actually, right? So that
Okay.
for exam point of view, derivation is not at all important over here. But you have to remember the final expression. From the final expression, you should know the significance. Actually, right? So you
Okay.
So, ma'am,
as
director to remember matrix.
yes,
So straight away it
ye-
is a formula. That's all.
yes, yes. As I've shown you this problem, right?
Okay.
I have
Okay.
shown you this problem. So you have to utilize. See, in this question, they have not given the what value. Okay.
Yes, ma'am.
So just try this problem. Just try to find out. See what they have asked in the three-dimensional strain stress relation for an isentropic material. They have also mentioned what is a material. Okay, and they have given this matrix. Now first you need to find out what kind of matrix is this. So this is an compliance matrix they have given. I can straight away say that.
Yes, ma'am.
Okay, now you have to recall the formula the just now you have studied, right? What is the formula? It was like so I can say this A can be of
1,
uh,
ma'am.
yes, but in ahead of that you have 1 by E, right?
Yeah, yes, ma'am.
Right, so I can say A value is 1 by E. What will be the C value? Minus mu
Minus mu by E, ma'am.
minus mu by E. Okay, now what is the B value?
It is 2 of 1 plus mu by E, ma'am.
2 of 1
plus
mu
mu by
by
E.
Right, this value I got my A, C, B. Now they have said that how these are dependent constant, which one is correct. Now you have to substitute this value and you have to check which one is satisfying.
Okay,
Simple
ma'am.
thing, very simple, but you have to have a knowledge about what is A, what is C, what is B. Right, now you
Sure.
substitute in either of this. Like for an example, if I want to substitute for the first one, that is minus mu by E, right? So I must solve that 1 by 2E minus 2 1 plus mu by E. Now if I want to solve this thing, I must get it should be equal to C value, right?
Yes, ma'am.
So you have to find out trial and error method you have to do, and you have to find out the result. Just find out the right answer.
It means, ma'am, all four options you have to check.
All 4 options?
We have to check, ma'am.
Yes, you have to check all the 4 options.
Ma'am, D, ma'am.
D.
Yes, ma'am.
So D you are getting that it is equivalent to, let's check. So A is our 1 by 2E and B is around this is B divided by 2. So I will be getting 1 minus this by E. I can write.
Ma'am, D. Option D. Last option, ma'am.
Yes,
Fourth
yes. So I can write like this. If I want to substitute the value, so 2E you will get 1 minus again 2 minus of 2 mu. How you are getting D?
option. Ma'am, it's D. Last option.
This option?
Ma'am, D option. C is equal to A minus B by 2.
How you got that? That only I am asking.
Ma'am, A by 2 is A is 1 by E and B by 2 becomes 1 plus mu by E.
Okay.
And
I just okay. Equals to A was 1 by E and B by 2 was 1 plus
1 plus mu by E.
So that 1 minus 1 minus mu, this will get cancelled, you will get as minus mu by E, right? That is equal to C. So likewise you have to find out. So done.
So ma'am, we have to remember this matrix for orthotropic material and isotropic material only.
Actually, I will suggest you to remember for an isentropic alone. Okay, for isentropic I have shown you both the stiffness and the complaints, right? So because further this is connected with an principal stress and principal strain. Okay, so all the principal stresses and strain will be compiling with an isotropic material, right? So further it will be reduced. Okay, so you can remember only this isotropic material. Okay, but for the number of elastic constant, right, you have to remember that. But in case they ask for orthotropic, right, so please I suggest you to remember both the orthotropic as well as the isentropic. I know that it is little complex, but try to remember that. Okay. Right? Shall I move? So all of you are getting this answer D?
Yes, ma'am.
Alright. So, right. Now we will come to the another very important, right, as a plane stress. Okay. So as a plane stress. So do you have idea what is plane stress? What is plane stress? Anyone? What is plane stress? It plays a very
Multiple different loads can be acting in a particular object, ma'am, but the amount of stress that is experienced in a single plane is called as a plane stress, ma'am.
Okay. So, alright. So basically, it's all about the states of, we can say states of stresses. Okay. So when we say the stress of stresses, that means we have seen, these are the various types of stress of states. Now it will see that now this is for the 3D plane, whatever we have seen for the 3D plane. Now what will happen when to simplify some kind of complex problem, right, from 3D we will convert into terms of 2D. So when we are converting the terms into 2D, right, the problem becomes much simpler. And what kind of problems that we can use in the time of plane stresses? That means when one of the component or one of the stresses will not act in another direction. For an example, if the stress and stresses are acting on x plane and y plane, in the z component we will ignore it. So on that kind of scenario we will take as a plane stress. Now when we can ignore, there are two ways. Either it is not acting or we are neglecting, we can neglect it, or the thickness is very small that we can neglect it. Okay, so these are the possible ways when we can neglect it. Okay, so is it clear? That when we can neglect the stresses? So what happens, suppose for this particular diagram or figure we are considering the x and y. Okay, the stresses is acting on the x and y, that is no other no stresses is acting on the perpendicular direction. Along this perpendicular direction, that we are not considering any kind of stresses. The reason behind, the thickness is very small. So whenever any component where the thickness is small or negotiable, right, so the small amount of stresses, if it generates and we ignore it, so such kind of problem we can solve using the plane stresses. Okay, it defines that there will be some amount of normal stresses. We have already seen some amount of normal stresses will be there, normal stresses and shear stresses only on the xy plane. Okay, in the z plane we will ignore it. In the z plane, whatever will be there in the z plane, the stresses acting on the z plane will be considered to be a 0. So suppose based on the previous configuration, so we can say that in this plane stress condition, the sigma along the z direction or z direction will be considered to be a 0, and the shear stresses acting on xz and the tau yz, or I can say zx or tau zy will also be 0. Okay, when such kind of problem statement we can solve using the plane stress problem. Right? Similarly, when this things will become 0, now we have to see how the change in strain occurs. But the strain, if I want to consider sigma zz, will not become 0, but the sigma xz and gamma xz or gamma yz will become 0. The strain with respect to xz plane and strain with respect to yz plane will become 0. Right? Noted? Please let me know. Yes.
When the shear stress along the YZ and then XZ planes are 0.
Which is around the
No, sorry. 1 second. Yes, ma'am. Why that epsilon ZZ is not equal to 0?
epsilon zz, because there will be some strain will be occurring. Okay, along this plane there will be strain will be occurring due to this effect. Either it is negative or positive, whatever it is, but there will be some strain.
Which means there is also some stress in that particular Z
No.
direction.
So that is a consideration, that is an assumption for the plane stresses. Okay, so the main motto of the plane stress is to convert the 3D problem into 2D problem. Okay, now what are the considerations that they can transform the plane? Okay, so mostly if any problem where the thickness is very small or negotiable, okay, that is a main constraint of the problem. As they have given an example, thin plate with a central hole, okay, or any kind of circular plate with a thin circular plate, it should be thin. Okay, the thickness is very small. So in that kind of consideration, the sigma z, see, this is theoretically we are speaking. Okay, so practically is something different, we all of you know, right? So theoretically, to solve this standard form, we will consider as that there won't be any kind of particular stresses, like perpendicular to the plane stresses, there won't be any stresses, that is z plane, no stresses will be occurring. Okay, right? So in that configuration, this is the scenario. The similar way, when we will see for the plane strain, okay, plane strain problem. Okay, so plane strain problem can be used when again some kind of complex problem we are transforming from 3D to 2D problem. We are simplifying. All we are going to do is in form of 2D. But here the constraint is in the component which you are going to convert in 2D. There should be some difference in thickness, right? There should be some difference in thickness. For an example, we can solve such kind of problem where the we can say where one of the thickness is very thin and another side of the thickness is quite larger, right? For an example, long cylinders. Okay, if we consider long cylinder, what happens if the diameter is small as compared with the length of the cylinder, right? So when there is a pressurization is occurring or any kind of loading system occurring into that particular object, so that kind of problem can be solved using the plane strain. So in this plane strain, what it says that, okay, consider again in an xy plane. Again they are considering the xy plane. So the normal stresses strain will be acting on it. Okay, normal strain will be acting on this xy plane, but here the configuration something like this. If z plane or the perpendicular plane, okay, is considered to be as 0, right? Along the z plane, the strain will become 0 here, but there will be some amount of stresses acting on along the z plane, so it is not considered to be a 0. Just a reverse case what we have seen in the plane stress.
Plane stress. It's a reverse of plane stress.
Yes, it's a reverse of plane stress. But other parameters what we have seen, that tau xz and gamma xz and gamma yz, or I can say gamma zx or gamma zy will remains 0. Similarly, the tau xz equals to tau zy or tau yz or tau zx will be 0, right? This is the only difference, and this is the application. So plane strain is only can be applicable when there will be a different variation of thickness, and the variation is too large, like as compared with the diameter, the length of the cylinder is too long, right? So in that kind of problem statement, we can use the plane strain problem. Okay, so where the thickness is varying, one is a thin, another is a very thick. Okay, so on that cases, what will happen, the strain will be 0, but stresses along the z direction or the other direction, it will be there. But in case of very thin sections or thin plate, okay, what happens, there won't be in the perpendicular direction to this xy plane, that is a z plane. So there won't be any kind of stresses, but yes, there will be some amount of strain. Okay, so you can expect kind of assertive and reason question from this plane stress and plane strain. Okay, or they can ask you that which of the following statement is correct, or they can give you the examples of plane stresses and plane strain. So they can ask you that question like which of the following applications or the can be solved using the plane stress problem or plane strain problem. All right.
Ma'am, that tau xz, tau yz, tau zx and tau xy is equal to 0 in both plane stress and plane strain.
Yes, they are 0 in both the planes. Okay. Now we will see some of the again the matrix form. Okay, the how the plane stresses and plane strain, and how to solve. Here we will study about something like two another important facts. One is a compatibility equation, and second one will be your equilibrium equation. Okay, one is a compatibility equation and second one is a equilibrium equation, right? So for the plane stress, as I've said, for plane stress, as I've said here, sigma z, tau zx and tau zy will become 0. Okay. So in this regard, I can write sigma x, sigma y and tau xy. Okay, because if I want to use this thing, right, these terms are 0, these terms are 0, right? So I'll have to take the remaining terms. So equals to E by 1 minus mu square, okay, into, these are the 3 cross matrix, 1 mu 0. Then if this is mu, then this will also become mu, then this one becomes 1, this will become 0, other these two terms will become 0, 0, then this one will become 1 minus mu by 2. Okay, and here we'll have epsilon xx, epsilon yy and gamma xy. So whatever the z plane, the factors will become 0. All those factors will become 0. Right? So from this, what we can write, the sigma xx can be written as the equilibrium equation, that can be written as sigma E 1 minus mu square epsilon xx plus mu epsilon yy. Can I write? Similarly, how I can write sigma y by E by 1 minus mu square epsilon, now
Epsilon xx into mu
mu,
plus epsilon yy.
yes. Now how I can write tau xy, E by 1 minus mu square 1 minus mu by 2 gamma xy. So again, this value is a matrix, stiffness matrix. Okay, so this is the stiffness matrix. Shall I proceed to next?
Yes, ma'am.
Okay, then we will have for n epsilon xx, epsilon y, gamma xy right? 1 by E, right? 1 minus mu, then we will have 0, then again we'll have minus mu, 1, 0, 0, 0, and we'll have twice of 1 plus mu. Now what is mu? Mu is a Poisson's ratio, okay? Please do remember that, Poisson's ratio. So we have sigma xx, sigma yy, and tau xy. So from this we can write sigma xx, sorry, tau epsilon xx can be written as 1 by of E xx minus mu sigma y, then epsilon yy 1 by of E, then minus mu sigma xx plus mu, sorry, we'll have sigma yy, and gamma xy will represents 1 plus mu by E into tau xy. Okay. Now do you remember the relationship between this modulus of rigidity with an Young's modulus? Do you remember that formula?
Yes, ma'am. Yes, ma'am.
What is the formula?
E is equal to
Hmm.
2g of 1 plus mu, ma'am.
2g equals to 1 plus of
Mu.
mu. Now what will be then the g value? G can I write as E by 2 1 plus of mu? Can I write?
Yes, ma'am.
See here what we have. So what I can write? Can I write? It is tau xy by g. Right? Now next we will see what is the compatibility equation. Okay. What is the compatibility equation? You have to remember this compatibility equation. Just a second. This is the compatibility equation. So it is
Ma'am,
hmm?
excuse me.
Yes, please.
Why the compatibility equation is for this only, ma'am, plane stress? Why not
Ac-
for like a 3D, and why not for planes?
See, this is a compatibility equation. It's like combination of what are the plane stresses and the equilibrium equation. Compiling that, there's some kind of boundary conditions. After applying, they got this equation actually. Okay, but here this is the main motto of this plane stress and the plane strain is only for the 2D plane. The main motto is to convert that whatever it is acting, it will be on the form of 2D, right? So that's why we don't have any sort of third degree like z point, and the point is z is 0 here, like sigma z is 0.
No,
So
ma'am,
there
for
is,
what purpose this is used, ma'am? Compatibility equation.
for compatibility equation is like, for an example, you got some kind of elastic problem, okay, some kind of constraint, so you will have some equations, right? So that equation you are going to break down and find out what are the unknown constraint parameters. Okay, for an example,
Like
I will show you one problem. Okay, uh,
partially differentiation.
yes, yes, uh, right, yes, see this question. Okay, so they have given that what is the equation that along the x direction and what is the strain in y direction and in the xy plane. They have given some in the form of equation. Now using solving this, you will know what is the stress strain field is occurring in between the particular object. Okay, so using this compatibility equation conditions, you can find out the parameters.
Okay. Okay.
So since we have came to this particular thing, let's solve this problem. Okay, so so see what they have written. And one more thing, though they have written the plane stress and the compatibility equation which I have shown, that is dou square sigma x by dou y square plus so on,
Strain,
which,
ma'am.
yeah,
Yes.
this is both are same for both the plane stress and plane strain. The compatibility equation will remain same for both. Okay, both will
Okay.
finally, when we solve that, both will satisfy the compatibility equation, but their equilibrium equations will be different. Okay, equilibrium equations are different, but when they are bringing to an compatibility equation for a two-dimensional state, okay, so it will be same, right? This is another kind of important point. So let's solve this problem and tell me the answer.
Ma'am, B is equal to 4A.
Which one? 4a, b,
Yes,
d.
ma'am.
Yes, ma'am.
Okay, so all of you are getting the same answer, so you have to use this formula.
Solve them.
Okay, so this is a question they have asked in 2000 last year. They have asked in last year. Okay, so you know what is the sigma xx value. You have to differentiate twice, you will get the value, and again you have to differentiate it twice, you will get the value of this sigma yy with respect to x. Okay, and this one with respect to y, and gamma xy you have to differentiate with x and then y. Then you need to substitute the value, you will get the answer.
B, ma'am.
Yes, D is the right answer. Okay. Simple problem, but if you don't know this compatibility equation, you won't be able to find out this, right? So in sometimes they will ask you to find out the unknown parameter. They might give you some equations. Okay, so they will give you some relations and they will ask you to find out what will be the value of b, or what will be the value of this thing, other parameters. Okay, so you have to be ready with these things. All right.
Excuse me, ma'am.
Yes, please.
I didn't see the answer properly. Sorry.
Okay, okay.
Okay. Actually, I got it as 4a is equal to 2b, ma'am.
4 equal to 2b. Just check your answer once again. Because when you differentiate this with respect to y, okay, sorry. Okay, so you will get this single differentiation will get this 2a, right, to ay. Now further,
Ma'am, the last term alone, ma'am, the RHS
See.
value alone.
see, we have to do it. Will be 2ax, then 2a, then this one will be first we're differentiating with respect to x, right? Give me x, then you will get by, then differentiated with respect to y, you'll be getting b, right? So what is the form? 2b equals to 2a
4a.
plus 2a, right?
Yes,
That's
ma'am. So
4a plus
b
2.
is equal to 2a.
Huh. Right.
Second option.
I just forgot to mention the answer. Just a second. Let me check it, okay? Just give me a while. Let me check the answer and tell you. Okay, I will tell you. Mostly, the answer should be something relevant to that only. Okay, just a second. 1 minute.
Ma'am, may I know the question number of this one, ma'am?
Question number of
Question number in GATE 2020 paper.
I think it was something 9 or 10 something it will be.
9 or 10. 1 second. Can you give me 2 minutes of time, ma'am, please?
Yes, sure. Okay. Oh, okay. There is some mistake. One mistake is there. Just check the answer if you got. The formula is dou square gamma xy by dou y into dou x. Okay.
Then it will be 4a, ma'am.
The 2 is not there, ma'am.
Yes,
two is
yes. 2
in
is
equation.
not there. Okay.
Okay.
2 is not there. Right. So
Okay.
please correct that. Please correct it here also. 2 is not here. Okay. 2 is not there. Okay. 2 is not there. So then it will be b equals to 4a, right? Right, 2 is not there. Okay. So now we will move to the plane strain thing. Okay. So plane strain, what are the facts we have seen? So here there will be no strain, then xz and yz will be 0, right? sigma is not equal to 0 in case of plane strain. Now first I will write, in case of plane strain you have to remember the stiffness matrix. Tau xy equals to E by 1 plus mu 1 minus twice mu 1 minus mu, then mu, then 0, then mu 1 minus mu 0, 0, 0, 1 minus 2 mu by 2. Epsilon xx, epsilon y by gamma xy. Okay. Have you noted?
Yes, ma'am.
Alright. So similarly for this one you can find out what is the value of sigma xx. What will be the value of sigma xx here? How you can write? E by 1 plus mu by 1 minus of 2 mu 1 minus of mu sigma xx plus mu epsilon yy, then sigma yy E by 1 plus mu by 1 minus of 2 mu epsilon xx plus 1 minus mu epsilon yy, right? Then tau xy represents E by 1 plus of mu 1 minus of 2 mu 1 minus 2 mu by 2 xy.
Ma'am, sigma yy is equal to E by 1 plus mu into 1 minus 2 mu into that strain xx value, ma'am.
Sorry,
Mu into epsilon xx, ma'am, for the sigma
which one you're
yy.
telling?
For
Which
sigma
value?
yy, ma'am.
Sigma yy equals to
Sigma yy
sigma yy.
equal to mu into
Okay.
epsilon x.
Okay. Mu is missing. Okay, that's great. Mu, noted. Just let me know once you have noted.
Yes, ma'am.
Alright, we'll move to, okay, please note down this table, right? How this conversion process takes place. Okay, so when the from plane stress to plane strain, the E value and the nu value, okay, these are the nu. for plane stresses to plane strain and plane strain to plane stresses. Shall I move to next?
Ma'am, one
Just a-
minute, ma'am, please.
Okay.
Yes, ma'am.
Okay. Next comes, this is the equilibrium equation for equilibrium equation for the entire body, okay, along the XYZ plane, okay, when no body force is applied or considered. Okay. So you have to remember this basic form: dou x plus dou tau xy by dou x plus dou tau xz by dou x to 0. This is a standard form, okay, standard form of equilibrium equation. Then dou tau by x by dou y plus dou sigma y by dou y plus dou tau y z by dou y equal to 0. Then dou tau zx by dou z plus dou tau zy by dou z plus dou So this is the equilibrium equation. So whenever the z components will be 0, so this values will be ignored. Okay, this values will be ignored. So this is the equilibrium equation without body forces. So this is along the x direction, y direction and z direction. Okay, so I request please mute yourself, okay, until it is required. Okay. All right, shall I change?
Yes, ma'am.
Yes, ma'am.
Okay, so we have solved this problem. Okay, so there are some Airys stress function, okay, so which is quite connected with an plane problem. So what I said as an plane stress, so it should be, the thickness should be very small when the plane is undergoing, right? So such kind of problem can be solved using the plane stress. But in case of plane strain, what happens, the thickness will be varying from one another, right? And so in that kind of scenario, the plane strain will be taking, right? But Airys stress function, especially this Airys stress function, this is one of the method of solving any sort of static linear elastic problem. Okay, so this is also can solve 2D two-dimensional problem, be static linear elasticity problem. Okay, it solves static in the sense that without any change in the time constraint, right? So linear elastic problem can be solved using this Airys stress function. Okay, and this Airys stress function is also implemented for an isotropic material. Okay, isotropic material. Okay. But as we have seen previously with the equilibrium equation, but here there are some certain problems where it can also find out with any forces acting on it. So it can be considered with body forces. Okay, so either it is the body forces there or not there. So this, using this Airys stress function, especially by adding the body forces, we can solve the problem, right? And based on the boundary conditions, by applying the boundary conditions, like what kind of loading system or all those parameters we can take into consideration, putting the boundary values, and we can find out the value. Okay, so here you need to remember this basic forms. Okay, so first, when the Airys stress function or Airys function they say, that means you have to remember this formula. First of all, you have to remember this formula, right? What is sigma x? Okay, sigma x represents dou square phi. Okay, any stress function defined by the letter phi. Okay, whatever the function, okay, it will represent by the letter phi. So to find out the stresses acting the x, y and xy plane, so you have to use this formula, right? Please note down the sigma x equals to dou square phi by dou y square, dou sigma y equals to dou square phi by dou x square, and tau xy represent minus dou square phi by dou x into dou y. Okay, so as we have seen our equilibrium equation, right? So what happens in the equilibrium equation? We have seen that all the z components become 0. Where all the z components become 0, so we get a equation something like this. Okay, we get the equation something like this, right? So that can be converted in a biharmonic governing equation. So you don't need to know that how this derivation has been appeared, right? So you have to remember this harmonic equation. This can be written as dou power 4 by 4 phi by dou x power 4 plus dou power 4 phi dou y power 4 equals to minus 5 by dou x square into dou y square. Please note down this formula. Okay. So more
The same thing is represented here also, no, ma'am, by harmonic governing equation.
yes.
Oh,
This is actually Laplace equation, right? So this will satisfy the Laplace equation,
okay.
right? Shall I move to next?
If it satisfies, then what you told, ma'am?
If it satisfies means actually it will satisfy, this added stress function will satisfy. Suppose, as I've said, they will be giving you some equations, okay? So you can find out the unknown constraint parameter from here, okay? You have to solve any problem, you have to see whether it is an isentropic material means it, and if it is a, you are solving in a linear elastic problem, then it has to satisfy. This is a basic assumption, okay? So once you find out this parameter or equation, you can find out the unknown constraint value, okay? We will see how to find out this unknown constraint. So I think this is a problem, okay? Again, this is one of the problem. Which one of the following conditions to be satisfied for an equation? They have given the equation, that is phi equals to ax power 4 plus b y power 4 plus c x xy cube to be considered as an Airys stress function. Now sometimes what they will do is, here they ask you to find out the equation, right? But some other time they will give you the constant value, suppose the value of a, value of b, value of c, and they will not give you value of a for an example. So from that you have to find out the value of a, what is the value of a constraint. So likewise you have to find out, okay? So sometimes they will give you the equation, you have to form what is the Airys stress function, then you have to apply the boundary condition and you have to see what kind of factors or the changes will take place, okay? Got the point?
Yes, ma'am.
Okay. Now in this equation, just see, they have given the phi value. What I have said, the equation, the formula was sigma x was am I right? It was dou square phi by dou y square. I think this was the, no, there is a y, it will be alternative. Okay, square phi by dou x square, then tau xy will becomes minus phi by dou x dou y. And next was dou power 4 phi by dou y power 4 plus 2 by 4 phi. So simply you need to keep on differentiating and you will get the answer.
A plus b is equal to 0 now.
A plus,
A plus b is equal to 0.
just wait, I will see the answer, okay? Yes, because finally you will be getting 24a plus 24b plus 0 equal to 0. So you will get a plus b equal to 0.
Can you tell how to do this one? So,
Very simple. See, this is a, you need to satisfy, okay? They have said already you need to satisfy. So this is a equation. You no need to use this formula here, okay? There will be some problem, you need to use this formula. But here in this problem, you don't need to find this. So what you are going to do is, you are going to differentiate this equation with respect to x, respect to y, okay? So
okay,
one, so once you get whatever the values you will get, you need to keep on substituting over here, right? This is the equation to satisfy.
Yes, ma'am. Yes, ma'am. Got it.
So when you will differentiate this dou phi by dou power 4, you will get 24a, and when you will solve this dou power y power 4, you will get 24, you will get 24b, right? And when I solve dou power 3 phi by dou x by dou y squared, you will get 6cy. So further you differentiate with respect to x, it will become 4 phi by dou x squared by dou y squared, it will become 0, right? Substituting over here, you will get 24a plus 24b plus 0 equal to 0. So 24 by a plus b equal to 0. You get a plus b equal to 0. So I will share the solution, the last year the questions what they have asked, right? I will share in our WhatsApp group, okay?
Okay, ma'am.
Yeah. Right. Okay. Similar kind of problems you can expect. See in this problem what they have said, that sigma x value has been given, sigma y value has been given, and sigma xy. So instead of tau xy they have given as sigma xy, and you have to find out the unknown coefficient value, right? So how you can use, you know this formula, right? You know, once you know the sigma x means what, dou square phi by dou y square, right? So you know how to apply it, okay? Apply and apply under this equilibrium conditions, and you will get the unknown parameter. Okay, so you can note down this question and you can solve, right? Please note down this question. So write down these questions. So again, see the question, it is a plane stress condition. So this is a problem based on the plane stress, okay, and absence of body forces. So absence of body force means you have to use an equilibrium condition. Shall I change to next? So you can solve this in your home, right? Just note down the question. And this is a very important topic. Every year they are asking the question from plane stress condition, transformation, then Airys stress function, right? So maybe the procedures, the small definition, right? So you have to be alert. Can I change to next?
Yes, ma'am.
Okay. So again you can expect such kind of problem from an plane stress problem, okay? So they will give you the sigma xx value, sigma yy value, and sigma xy. Instead of tau xy they will give you sigma xy, okay? And you need to calculate the sigma z, right? So again, you know the formula, right? You know the that plane stress means what is a formula, and what is a formula for the sigma zz, right? So you can solve that, because sigma zz is not equal to 0, right? So you know the formula, solve it, and you will get the answer, right? So epsilon zz is a formula of minus mu by E sigma xx plus sigma yy. This is a formula, right? Mu value is given and E value is given, right? So you have to substitute the values and you will get the answer, right? Now try to solve this problem.
A, ma'am.
A.
Yeah.
Okay, all of you getting the same answer?
No, ma'am. It's D, ma'am.
It's a D,
Minus.
because here also we have minus.
Minus, yeah, ma'am.
Right?
Option D.
Yes, option D is the right option. See, as I've said, gate what they do, see the same answer. 3.75 10 power minus 4, here also 3.75 10 power minus 4, but the difference is minus. So if you do a small mistake, right, so minus plus, you will get a wrong answer, right? So gate, they do the same thing. So if it is 2 marks, means your 2/3 marks will be gone, right? So please understand the system and try to avoid these silly mistakes. Do not hurry, right? Look into the minus, plus symbol and everything, and then proceed forward. Okay, next. Okay, this is also another problem based on Airys stress function. See, here they have given that what is the function they have given here. Okay, so they need to find sigma xx, sigma y, and tau xy. Okay, so you know the formula, already have discussed what is the formula for the Airys stress function. Just you need to differentiate with respect to the parameters, and you will get the values, and you have to find out the answer, right? So please solve and tell me this answer. Solve and tell me the answer. What is sigma xx value? Dou square phi by?
Ma'am, that is first one, ma'am, option.
First option.
Yeah, ma'am. Sigma x is 36x square.
So you will get all of you getting the same? So sometimes what you have to do is, now you are finding the sigma xx, right? And see this values, if you find that sigma xx value is 36 x square y, right? And here you are not getting any kind of plus or minus, it is getting plus. So straight away you can select this option. You don't have to further calculate and find for other parameters, right? Because if there are other option which is consider same thing, right, then you need to take care of it, right? So likewise you can also save your time. So confirm me, are you getting the same answer, the option A?
Yes, ma'am. Option A, ma'am.
All right. So yes, sometimes they can ask you the question something like this, find out this biharmonic equation in expanded form of Cartesian coordinates. Okay, so you have to find out what is a harmonic form, right? Already we know is a C.
C.
Option B, ma'am.
C, ma'am.
C.
Yes, ma'am. Yes, ma'am. Option C, ma'am. Correct.
C. Right. So likewise you can this is one of the steps. Okay, so how to solve the Airys stress function in the real approach, right? So this approach I will be giving you in the notes, that how to find out, right? So so likewise option also you can expect, okay, right? So you can also expect such kind of questions like how to solve step by step procedures. Okay, so these procedures I will give the layout in the notes. Okay, since we don't have much time, so I will just provide. Okay, that's a theoretical thing. Like, so once you solve, you can find out this answer, right? Okay, so any questions, just let me know. Any doubts? So we can, otherwise we can wind up the session.